Let's discuss Unit 8 Theory of Computation and Compilers Solutions. Which of the following is the function of the semantic analysis phase of compilation process? Let's see the phases of compiler first. We have lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, then code generator and code optimizer. We will see the options in the order of the phase. Tokenization is associated with lexical analyzer. This is the process of breaking the input text into a sequence of tokens. That's why after the lexical analysis phase, the token stream is entering as the input to syntax analyzer phase. This option is not related to semantic analysis, so we will rule it out. Next, we will see about type conversion. Implicit type conversion usually occurs in the semantic analysis. Type checking is also an important part of semantic analysis. What is actually type checking? The compiler makes sure that each operator has matching operands. Say for example, if you add 5 plus 3, this will give you 8. What happens if you add 5 plus a? Here the compiler will give some kind of error stating that the operator plus doesn't have proper operands. So here it is 5, int is fine, but this is not fine. So this type conversion, type checking, everything is a part of semantic analysis phase. Option number 1 will be the right answer. What about the other two options? Loop optimization is a part of code optimization process, but this code optimization belongs to mission independent code optimizer phase. Loop optimization is the process of reducing the overheads associated with loops. When you learn about loop optimization and peephole optimization, loop optimization is concerned with mission independent code optimization and peephole is concerned about mission dependent code optimization. What about data flow analysis? This is actually occurring in the code generator phase. It helps in improving the efficiency of the code generated by the compiler. Where is this analysis performed? It is performed on control flow graphs. Determine the information regarding the definition and use of data in program. With the help of this analysis, optimization can be done. After code generation, we have code optimization here. So this particular analysis will be helpful in code optimization is what this point says. So you know now all the 4 options are belonging to one or the other phase. Next question. The number of tokens in the following line. What are actually tokens? In tokenization, we saw it's a process of breaking a statement into token. So here we will break it like this. We have for, I, in, range, open bracket, begin, end, step, close bracket and a colon. Just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Option number 4, 12 will be the right answer. So when you give this particular statement to the compiler, first it will create a set of tokens in lexical analysis phase. So this set of tokens for, I, in, range till the colon in the last will be given to the syntax analysis phase. So what is the first step it will do is it will remove all the white spaces and whatever recognizable minimum unit called as token is found, that will be separated like this. So the number of tokens will be every individual unit. For, in, range are keywords. When something comes between for and in, it knows it's a variable. So this is a variable. Similarly, in this format, we have a variable again, beginning variable, ending variable. Similarly, the step is also a count. Say for example, when I say 1 is to 10 is to 2 or A is to B is to 2. So this is the beginning of the range, this is the ending of the range, this is the number of steps it has to go. 1, 3, 5, 7, 9, in the range 1 is to 10 is to 2. This is how it will go on. Next question, an ambiguous grammar is one which has. Ambiguity means it should have more than one meaning or more than one form. A context-free grammar is said to be ambiguous if there exists some string that has at least 2 distinct derivation trees. Different derivation is what they have mentioned as distinct derivation. Alternatively, we can tell ambiguity implies the existence of 2 or more leftmost or rightmost derivations. Actually, certain books stress that only leftmost derivations are counted and parse trees are counted. Definitely B is there. So based on this point, we can conclude option 2, B and C will be the right answer. And ambiguous grammar will have more than one leftmost derivation or more than one rightmost derivation. Next question. The following code, statement is equal to if expression then statement else statement, or if expression then statement. This particular code suffers from what? Lambda moves. This is not going to be with the following process, so we will remove fourth option. Left factoring is not a problem, it is actually a solution, so we will remove 2 and 4. On seeing the input, we cannot immediately tell which production to choose to expand statement. Here also you have if expression, here also you have if expression. When there are more than one way to represent something, this is ambiguity. Option number 1 will be the right answer. So this particular code is taken from the topic eliminating ambiguity in syntax analysis. You can refer compiler design books. So this is actually a solution type. So in this solution they have told how to solve this ambiguity issue. Next question, shift reduce conflicts are resolved by. So what is shift reduce first? It's a bottom up parsing method. There are actually 4 possible actions the parser can make. First action is shift. It will shift the next input symbol onto the top of the stack. Reduce. The right end of the string to be reduced must be at the top of the stack. Locate the left end within the stack and decide with what non-terminal to replace the string. From the production rule of the grammar, we will be deriving strings. That is top-down parsing. In bottom-up parsing, we will be given the string and we should get to the non-terminal part, the production rule part, by parsing it in bottom-up fashion. So here we have to take a particular string and then decide what non-terminal to replace. So usually from non-terminal we will be deriving string. Here from the string we have to place the non-terminal. The next action is accept. Announce successful completion of parsing and error. Discover a syntax error and call an error recovery routine. Now where does the conflict arise? There are context-free grammars for which shift-reduce parsing cannot be used. Every shift-reduce parser for such a grammar can reach a configuration in which the parser cannot decide whether to shift or to reduce. It doesn't know whether it has to shift the symbol to the stack or to reduce it to a non-terminal. That case is shift-reduce conflict. Or it cannot decide of several reductions to make. There may be multiple productions leading to multiple non-terminals sometimes. That is reduce conflict. Technically, these grammars are not in the LRK class of grammars and are referred to as non-LR grammars. When the parser cannot decide whether to shift the input symbol to the stack or whether to reduce the string to a non-terminal, such kind of conflict is what we call a shift-reduce conflict. When they cannot decide something, it means they are actually ambiguous grammar. Shift-reduce parsing can be adapted to parse certain ambiguous grammars. So when there are several reductions in ambiguous grammars, what technique does it use? It uses precedence and associativity. Conflicts are resolved by precedence and associativity. This will be under the topic ambiguous grammars. In that we will have a subtopic, namely precedence and associativity to resolve conflicts. And so we are going with option number 4, associativity and precedence. Actually it should be given as precedence and associativity. We have precedence of operators, which should come first and which should come next. So if there is a plus, there is a multiplication, I have to choose multiplication. This is precedence. What is associativity? When there are 2 or more plus, which order should I follow? When there are 2 or more same operators, we adopt left associativity. We have 2 plus 3 plus 5 means we will first start with the left side. 2 plus 3, then 5 plus 5. This will give 10. We will approach this way. In order to overcome this ambiguity problem, it will adopt precedence and associativity technique. Actually, why is the conflict arising? It is because of ambiguity. It is the reason and it is not a resolution technique here. What about the other two options? Left factoring is a transformation that is useful for producing a grammar suitable for top-down parsing. It is not a content of bottom-up parsing. What about left recursion? Left recursion elimination, so it is not a technique. Actually, we have to eliminate that. And left factoring are useful for rewriting grammars, so they become suitable for top-down parsing. Both these terms belong to top-down parsing, and in fact, this particular term has to be eliminated. So this is not a technique. Maybe this is a technique to give a suitable grammar for parsing, but this left recursion is actually a problem. This is a solution and this is actually a problem. Eliminating the left recursion will be a solution. Next question. For regular languages and context-free languages, which is not correct. So here's the table. For union operation, regular and CFL are closed. So this is true. For concatenation, they are closed. I'll just mark this for easy reference. It is true. Both are closed under intersection operation. They are not closed under intersection operation. Both are closed under complementation operation. Same case, they are not closed. Both are closed under clean star operation. Yes. Find which is not correct. Option 3, C and D will be the right answer. Next question. The language of the following push-down automata would be. For regular languages, we have DFA and NFA. Deterministic finite automata and non-deterministic finite automata. For context-free languages, we have push-down automata. All the four options given here are context-free languages. They have given few transitions and they have asked to find the language of the push-down automata. In push-down automata, we will be using stack. Del current state next input symbol top stack symbol is equal to new state and stack symbols. If we take the first one, we have Q0, A and Z0. Current state will be Q0. From Q0, when we read the symbol A, at that time, the top stack symbol will be Z0. So when I read A, when I am in Q0, what will happen? I will still be in Q0, but along with this Z0, 3 A's will be pushed to the stack. The top stack element will lie in the rightmost corner and whatever is given in the front will be the newly pushed elements. The stack is initialized with Z0. So this is the initial stack configuration we can say. When A is read from Q0, 3 A's are inserted. Now what will be the top element? A will be the top element. The next transition, Q0 A comma A. It means I am still in the state Q0, but this time the top stack element is A. So again when I read A, this time there are already 3 A's in the stack. Along with that, so this A is staying same as this A. We have 3 more A's that are pushed to the stack. So let's add 3 more A's here. Altogether we have 6 A's. This is the second transition. What about the third transition? Q0 input symbol is B and the top stack element is A. So this is the top element. Now we are still in Q0. On reading input B, what it is saying, we are moving to the new state called Q1. You are just popping the top element. What is the top element here? It is this A. If we pop 1A, how many A's will be remaining? 1, 2, 3, 4, 5 A's will be remaining. So we will place the 5 A's along with the Z0 configuration. This will be in Q1 state. So far we were in Q0 state and now we are moving to Q1 state after popping it. Again from Q1 state, when I read B input with the top element as A, the top symbol is still A. Again when I read B, this A will be popped out and we have 4 more A's along with Z0. Still we are in Q1. So if we take 4 more B's, so this is 1B, this is the second B. For the third B, 1A will be popped out. For the fourth B, 1A will be popped out. For the fifth B, 1A will be popped out. And for the sixth B, the final A will be popped out. After 6 B's, the stack configuration will be again with Z0 and the state will be in Q1. When the current state is Q1 and there are no more input symbols to be read, with the stack symbol Z0 in the top of the stack, we are entering into the final state. This is what the final transition is saying. So the final state is entered along with the stack symbol Z0. So they have given QF is a final state. Based on this explanation, how many times A has been read? It has been read 2 times. How many times B has been read? 1, 2, 3, 4, 5, 6. So B has 6 reads. For every read of A, we are pushing 3 A's. For every read of B, we are popping 1A out of the stack. For 1A, we are inserting 3 A's. For the second A, we are inserting 3 more A's. So 3 plus 3 will be 6 A's altogether. How many B's are read here? 6 B's are read. So 6 B's will take out all these 6 A's, which says that number of A's pushed to the stack will be equal to number of B's that are read. Let's take the first option, A power n, B power n, where n is greater than 0. Let's take n is equal to 1. We have A, B as the first string. Now let's initialize the stack with Z0 and we are in Q0 state. Let's take the first symbol A. When it is Z0 and A, we have 3 A's to be inserted. So when we read A, 3 A's have to be inserted here. They have to be pushed onto the stack. Next symbol will be B. When I read B from Q0, what should we do? We have to pop exactly 1 A. So we will pop only the first A, which is the top symbol, and we will have remaining 2 A's along with Z0. Do you have any other input symbol? No. So we are entering the epsilon part. We are now in Q1 actually. Q1 with epsilon along with Z0 will take you to the final state. But do we have only Z0 here? No. We have 2 more A's, but we don't have any more B's to pop out these 2 A's. It means we are not entering into the final state. So the pushdown automata will not be having this language. One can be ruled out. Let's take the second option, A power n, B power 2n. Again we will go with n is equal to 1. For 1A there will be 2 B's. Let's again initialize the stack with Z0. For the first symbol A, we are in Q0 state. When A is read, 3 A's are inserted. For the first B, 1A will be popped out. For the second B, this is the first B and this is the second B. The second A will be popped out. So this will be popped out and now this will be popped out. We have remaining 1A and Z0. We are in Q1 now. So at this stage itself we came to Q1. Now just check Q1, there are no more input symbol, so we can take it to be epsilon. Do we have only Z0 here? We have 1 more A that has to be popped out, but we don't have any more B here, which means again we are not entering the final state. So this is also not the language of the PDA. Now let's take the third option, A power n, B power 3n. Let's go with n is equal to 1. Now we will have 1A and 3 B's. So what is the initial configuration? It is Z0. In Q0 state, we are reading A and inserting 3 A's here. After pushing 3 A's, for the first B, we are popping out the first A. So 2 more A's are here. For the second B, we are popping out the second A. 1 more A is present. For the third B, we are popping out the third A and only Z0 is present. Now the state is Q1. When the state is Q1, when there are no more inputs along with Z0, we are entering the final state, which means option 3 will be the language of the given push-down automata. Now just check this. The number of A's pushed will be equal to the number of B's read. How many A's are actually pushed here? For one read of A, we are pushing 3 A's. When I say there are 3 A's pushed, it means it is the number of B's that are read. So do we have 3 B's here? Yes. So this particular condition is satisfied only in option number 3. Now let's check option number 4 also. A par n, B par 4n. For n is equal to 1, we will have 1 A and 4 number of B's. When you take the initial configuration Z0 on input A, we will be inserting 3 A's. For 3 B's, we will pop out all the A's and we will have Z0. Still we have one more input, which is the last B. Q1 is there, B is there and Z0 is there. Do we have any such transition? No. Since we don't have such transition, it means this is also not going to go for the final state. This way also we can say option number 4 is wrong. By working with this transition, you have to find how many A's are inserted at a time. So how many ever A's are inserted, that many B's will be involved. So this will give the count of A and this will give the count of B. So when you take del of Q0, comma A, Z0, this is actually count of A. When we say it is equal to Q0 triple A Z0, this will be the count of B, which means for 1 A we are having 3 B's. When we have 2 A's, we will have 6 number of B's, which is the example that we have seen already. So this is how you have to interpret the transition and find out the answer. Now we will see the transitions for all the other 3 options. Let's take A par n and B par n. When we are in Q0 state with input A, we are inserting only 1 A along with the top stack symbol Z. So this is the top symbol. So we are inserting only 1 A. Again in the second transition, when A is going to be the top element. So already we have A here. When A is there, when I insert another A, this will also push only one more A to it. It means at a time only 1 A is pushed. When 1 A is pushed, we know that will be the count of B. It means for every A, there is only 1 B involved. When I say it is A, then there are 2 B's involved. When there are 3 A's, we can say 3 B's are involved. This will satisfy this particular language. If you take the other transitions, everything will be the same. For Q0 B comma A, we have Q1 with lambda, here it is epsilon. That's the difference here. The symbol has been changed. Similarly, the next transition Q1 comma B comma A will move to Q1 comma lambda. Here it is Q1 comma epsilon. Then for the final transition, Q1 epsilon and Z will give rise to QF, which is the final state. The last 3 transitions will stay as it is, while only the first 2 will have the change. Now let's see for A par n, B par 2n. For one read of A, we are inserting 2 A's. Similarly, for one read of A, we are inserting 2 A's. This rightmost part is the top element that we are referring in this part. So we have to not consider that. You have to take only the A's that are inserted towards the left side. Similarly, for A par n, B par 3n, we have 3 A's inserted for one read of A. Similarly, 3 A's inserted for one read of A. This set of transition is what is given in the question. Regarding A par n, B par 4n, we will have 4 number of A's for one read of A. Similarly, 4 number of A's for one read of A. See, when we arrange Z and 4 A's, A will be in the top and Z becomes the bottom symbol of the stack. So we have to understand the rightmost corner is the bottom. So this A is the bottom part. It means already one A was there. Above the A we have 4 more A's. You have to consider in this angle. This will not be the total stack configuration. It will be only with from the top they will say how many A's are inserted. So you have to know that difference. Next question. For the given two missions, which of the following is correct? Based on the options, we have to first find whether they are DFA. What is deterministic finite automata? Corresponding to an input symbol, there is a single resultant state. That is, there is only one transition. Let's check for the first mission. For state A, only one transition with small a should be there. We have a self loop with input small a. Similarly, we are moving to B for the same input small a. There are actually two transitions which contradicts the rule of deterministic finite automata. So this is not a DFA. When we know that this is not a DFA, we can say both missions are DFA is not going to be the answer. Now let's check the second mission. A to B involves A. There is only single transition. From B, we are moving to B again for A. From B, we are moving to C for B. So there are only one transition for each input. For C with input A, we are moving to B. For C with input B, we are again going to be in C itself. Again we have only one transition for every input. For A, we have A to B for the input symbol A. So corresponding to an input symbol, there is a single resultant state. There is only one transition. Then what about the first mission? It is a non-deterministic finite automata. If there is more than one possible transition from one state on the same input symbol, this is the case in the first mission. So this is actually NFA. From one state A on the same input symbol small a, we are going for two transitions, one to the state A itself and another to the state B. In this case we can say first mission is NFA. Now let's check whether they are equivalent missions. Instead of taking some sample strings, we will check certain conditions of the strings. We have transition for single A from A to B. So let's take this to be the first mission and the second mission. For the second mission, for the input symbol A, we are moving from capital A to capital B state. So the string can start with A here. What is the initial state? It is actually A here. Similarly, it is actually A here. Initial state will have the symbol of arrow mark with the state symbol, and final state will have double circle like this. So this will be the final state. In the first mission, B is the final state, and in the second mission, both B and C are final states. But in both the missions, A will be the initial state. Does any transition occur with input B from A? A does not have any transition with input B, so the string does not start with B for this mission. For the second mission, we don't have B transition from the initial state, so this is also not there. It is not about whether it is starting with B or not. We are going to check whether both the missions are going to respond in the same way. So regarding the starting point, they are actually equal. Now ends with A and B. So any string, if it ends with A, can be accepted. So we have a self loop in the first mission. Any number of A's can be accepted and the final A can take you to a final state. So taking this transition into consideration, we can say yes, it can end with A. What about B? Since B is having a self loop, we can say the strings can also end with B. What about the second mission? We have a transition from B to B with the input A. Can a string end with A? Yes, it can end with A. What about B? From state B to state C, we have a transition with input B, which is again resulting in a final state C. So based on this transition, we can say it can also end with B. Does it accept single A? Yes, it can accept single A because we have seen when it starts with it is already entering the final state. So this is fine, and even in this case we are entering into a final state, so this is also fine. Can it have only A's without B's? Yes, it can have only A's. So lots of A's can be self-looped with the state A in the first mission. So we have given the self-loop symbol here. So any number of A's can be taken, and the final A symbol can move to the final state. So this can accept a string with only A's. What about the second mission? We have a transition from A to B with A input, and there is a self loop on B. Again, this can also accept a string with only A's. What about the string with the A and a B? So for the first transition, we are moving from A to final state B. This is for input small a. When I self loop B, the string AB will be accepted. What about the second mission? From A, we are moving to state B for input A, and from B, we are moving to state C for input B. So AB is accepted. What about the string ABA? What is the difference between these two strings? Here AB stops, but here after B, is there a possibility to read A is the next thing that we are going to check. So let's have A, let's have B. When you take self loop, there is no possibility. So instead of the self loop, we will go for a transition again to state A with input B. This will give AB, and once again we will go from A to B for input symbol A. So this will be A to B to A. So A to B is A, B to A is B, again A to B will be A. ABA can be accepted because B is a final state. What about the second mission? Let's take A to B. We have A input here. Then for state C, we have B input here. From C, can I have a transition with input A? Yes, we can go back to B again with input A. Since B is a final state, ABA is accepted even here. The string has to start with A. Any number of A's and any number of B's can be followed after that. So both the missions are accepting all kinds of input. So we can mark option 3. Both are equivalent missions as the right answer. 2 and 4 can be ruled out. There is no case that it cannot be determined. While checking few strings, we can determine. Now let's check for A, B, B, A. Let's check for the first mission now. From A, we are moving to B state for input symbol A. We are looping once for the first B. For the second B, we are coming back to state A. For the next A, that is the final A, we are once more going to state B, which is the final state. So A, B, B, A is accepted here. What about the second mission? From A, we are moving to state B for input symbol A. From B, we are moving to state C for input symbol B. For the next input symbol B, we are going with the loop here. From C, we are moving to state B again for input symbol A. Since this is a final state, we can say ABBA is accepted. Like this, you can try for any strings. If you check for these two cases, you can mostly identify whether both the missions are equivalent or not. Next question. Arrange in appropriate order the construction of a finite automata. So we have 5 options here. Now we will restrict our order with these 3. It is very easy to construct a NFA with epsilon moves. In the sense, non-deterministic finite automata is easy to be constructed from some kind of regular expression. So let's take the NFA. From NFA, we can convert to DFA, deterministic finite automata. What we should do is we have to remove the epsilon kind of moves, and then there is a single resultant state corresponding to an input symbol. Let's take A here. If I have 1 as the input, it should go only to B. If it goes to C with 1, this becomes NFA. If you remove this part and make some changes accordingly, this becomes DFA. So there should be only one resultant state. B is the resultant state in this example, corresponding to an input symbol. So this will convert it to DFA. From DFA, we can get minimum state DFA. Sometimes we have to eliminate dead states and we have to make some other alterations to make it minimum state DFA. So this will be the order. What is NFA? It is C, DFA is E, and minimum state DFA is A. C, E, A. These two are not in that order, we will remove. Now from where did I say we are converting to NFA? From regular expression. 0, 1 star, 1, 1. It will be given this way. And from here only you will be converting to NFA. So this part is regular expression. We are converting to NFA. Before C, I have to place B. The order is B, C, E, A. Now the question is, after getting the minimum state DFA, do you write the problem statement, or from the problem statement do you get the regular expression? Which is correct? Definitely from the problem statement we will be framing the regular expression. From the regular expression we will be constructing NFA. NFA can be converted to DFA and the states can be minimized. This will be the right order, D, B, C, E, A. So D cannot be in the last part. In that case we will rule out 1 and we will mark option 2, D, B, C, E, A as the right answer. This is B and this is D. Next question, match list 1 with list 2. Undecidable problem is a decision problem for which it is impossible to construct a single algorithm that always leads to a correct yes or no answer. There is no specific algorithm. For some problems it will be decidable, for some it might not be decidable. What is a very popular example of undecidable problem? It is a PCP problem called post correspondence problem. Previous year question papers we have already solved few post correspondence problems. Please go through them to understand what it is. D is mapping to 2. The only option with D2 is option number 4. Let's then see about canonical LR parser. In a statement where they are comparing canonical LR and SLR parser, they have stated in the book as canonical LR parser may have more states than the SLR parser for the same grammar. This more state has been represented as large number of states here. So in this case we can mark C as 4. What about automata? Regular languages or CFL languages can be infinite. Regular languages have deterministic finite automata and non-deterministic finite automata. Similarly, CFL has PDA, push-down automata, or DPDA, deterministic push-down automata, to represent those languages. What is an infinite language? When I say it is AB star or A power n, B power n, where n is greater than 1, this is for CFL and this is for regular. In this case, can you say how many B's are there? It is infinite. Similarly, when I say n is greater than 1, it can be any n that goes above 1. So here also it is infinite. Only with infinite examples they would have proved pumping lemma property. We can map infinite languages with matching numbers to automata. What about backtracking? Backtracking in general, it's a powerful algorithmic technique that allows us to systematically search for solutions in a large search space. This search space will be called as state space tree, where there will be large number of states. So A can have an option of 4. There is a possibility. So this is with regard to general backtracking. With regard to this unit, recursive descent parsing may require backtracking. There is an option to backtrack, but in predictive parsing, this is actually a case of recursive descent parsing, no backtracking is required. In fact, this predictive parsing is explained with the idea of avoiding backtracking. The parser which said I don't want backtracking is the parser that they have given in the option. So A cannot be 3. Let's see another possibility of backtracking. In finite automata, we have a statement in one of the books. A non-deterministic algorithm would be able to solve the problem without backtracking, but a deterministic one can simulate non-determinism with some extra work. For this reason, non-deterministic machines can serve as models of search and backtrack algorithms, which means A might be mapping to option 1. Now let's check. A cannot map to decidable problems, so A2 cannot happen. Can A map to 4? Yes, A can map to 4. Can A map to 1? Yes, it can map to 1. Both are possible. Coming to B. When I want to represent infinite languages with matching numbers, I don't need any parser. It's not an undecidable problem and all, it's decidable. And they don't need large number of states and all. Once you design a particular automata, it should automatically work. So B is actually mapping only to automata here. Regarding canonical parser also, you can rely only on large number of states with respect to this point. Otherwise, this belongs to LR parsing and this belongs to LL parsing. So even C and 3 will not match. PCP is definitely undecidable problem. You cannot place it under any other category. So 3 options are correct here. We cannot go with any other option, and backtracking cannot go with predictive parsing. If we take this option to be no backtracking, then we can mark option 4 to be the right answer with A mapping to predictive parser. Next question, match list 1 with list 2. Let's start with a very known halting problem. Whenever we talk about Turing machine, we start with the halting problem. So D will be mapping to 2. D2 is available only in one option. Next we will see about recursive descent parser. Predictive parsers, that is recursive descent parsers needing no backtracking. Actually even here the statement is telling that predictive parsers need no backtracking. Can be constructed for a class of grammars called LL1. So from this we can map C LL1 grammar to option 1 recursive descent parser. Though they have mentioned about predictive parsers, they are still recursive descent parsers. Then we have 2 grammar productions in A and B. Let's check them. Chomsky normal form, a grammar G in which all productions are in one of 2 simple forms. Either A derives BC, where A, B and C are each variables. Variables in the sense we can tell them as non-terminals. A derives small a is where capital A is a non-terminal and small a is a terminal. Now just interpret option B. A derives BC or A. This is actually similar to A derives BC and A derives A. This is in the form of Chomsky normal form, and they have mentioned A belongs to T. It means a set of terminal symbols we can say, and A, B, C in capital, they belong to V. It means the variables part or the non-terminals part. So we can mark B to 3. So C is mapping to 1 and B is mapping to 3. What about A? A derives terminal and a non-terminal or a terminal, where small a belongs to terminal, capital AB belongs to the variables or non-terminal. Where do you find this kind of production? Greeback normal form grammar is one where every production body starts with a terminal. A context-free grammar is said to be in Greeback normal form if all productions have the form A derives AX, where A belongs to a terminal and X belongs to a variable. So this is exactly the form of A derives small a and B. In fact, when you get into context-free grammar, you have to go for a push-down automata. But here they have given as finite automata. Maybe when we convert this Greeback normal form to a regular expression, that regular expression can be implemented using a finite automata. In that idea, we can map A to 4. So is there any other option for A? You cannot map recursive descent parser, Turing machine. You cannot mark Chomsky normal form also. Since Fourth one is the only left out option for list 1A. We are going with option number 1 as the right answer. Again, this A4 can be taken to be right if this Greeback normal form grammar can be converted to a regular expression. That time it can be implemented by a finite automata. In that case we can take, or maybe instead of finite, if this is going to be just automata, we can take it to be a push down automata. You cannot have other options for the other three. Say for example, LL1 grammar can be mapped only to 1. It cannot be mapped to Turing machine. Similarly, it cannot be mapped to Chomsky normal form. And regarding halting problem, except Turing machine, you have no other choice. Grammar that is given in list 1B is perfectly Chomsky. So anything other than B3 cannot be considered again. So keeping all this in mind, we are going with option 1 as the right answer. With this, we are completing Unit 8 solutions.